Hello everyone, let's talk about another medium problem on Leetcode today, path with maximum goal, Leetcode 1219. In this, we are given a grid which of size m into n, uh, with each cell in this is mine as an integer, representing the amount of gold in that cell, 0 if it's empty. We have to return the maximum amount of gold we can collect under certain conditions. So first condition is that every time you are located in a cell, you will collect all the gold in that cell. From your position, you can walk one step to the left, right, up or down. You can't visit the same cell more than once. Never visit a cell with 0 gold. You can start and stop collecting gold from any position in the grid that has the same has same gold. That has some gold, sorry, not same gold. Now let's look at this example. We are given this grid 060587090, and the maximum gold we can collect is 9 through path 9, 8 and 7, which is giving us 24 gold. So now let's look at one more example. So suppose we start what you say taking gold from position 6. So it will be like we can go to 6 from 8, right? So it will be because we can go in 4 directions at a time. So it will give us 14 gold, and then we go to 7, it will be 23 gold. So based on where we start actually changes our gold amount. Suppose we start from 7, then we go to 8, which will give us 15, and from 15 to 9, it will be 24. So now that we have understood this problem, let's jump into the solution space. One way to solve this problem can be that because we need the maximum, we can think of it using like dynamic programming or something. But let's see why dynamic programming may not work. So let's look at this grid, which is given as an input. So suppose we go we start from element 6, then we go to element 8, right? And from element 8, we can go to 9, right? So at 8 grid 1 1, we can assume that okay, we are getting a sum of 17, because after 8 the maximum we can go is 9, right? Instead of 7 or 5 or some other path. So let's store this value in a cache somewhere, because dynamic programming is about memorization of the overlapping subproblems, right? But in this case, now we know that this is not the answer, but let's assume that this is our answer. Now we go to node 9. When we are processing this node, uh, we know that the maximum we can go for 9 is at 8, right? But we can't go back to the visited cell, because if we go to 8, if we go to 9, that means we have come from 8, and that means 9 is already visited. But all of this depends on this visited set, and we can't be sure which path we are coming from. Based on this, we cannot generate any caching strategy. So what I mean by this is, like, if we go to 9, the path, the node we have visited will be totally different when we are coming from, say, node 8 towards 9 or 7 or 5, whichever node. But because of this, we cannot employ any caching strategy. So what we can use here, and the answer to this is we can use backtracking. And before going into the backtracking, like why we have to do is like is basically we'll go into the example, but backtracking applies here because this is an algorithm which actually tries to incrementally find some solution, and if it ends up in dead end, it backtracks and then again starts from the previous solution which has worked so far. And why backtracking is not I mean, it's very similar to brute force, but it is separate or different in the sense that it eliminates some unnecessary exploration, and we will see at the examples how. And what it builds is something called state space tree, in which is like some kind of an n tree, where we at each step we will see n states, and based on that it knows okay whether it has find the solution, and backtracks if we have found some dead end. So it tries to build this search tree kind of a structure, and then with some finite states, and then backtracks, finding the solution. So now let's jump into the current problem. So let's look at how backtracking will work. So we can look at this array here, 06058799090. So first thing to note here is like we will always try to start from the points where there is some gold, right? For example, we can't go into the empty gold mines as per one of the problem conditions. So suppose we start from 6. This is just an example. What's the maximum gold we can collect from this point? So we can go to left, which will yield us 0. We can go to the right, which will again lead us to 0. So we will not go there. We can go up, but there is no mine at all. So we will hit the condition where we are out of bounds. So we will see -1 in this case. And then only sensible position for 6 will be to go to 8. And now when we have gone to 8, we can again go to left, right, up and down, because those are the only 4 directions allowed. And we go to first we go to like left, then we get 5 again, right? And we can choose minus, like we again go to different conditions, and we actually see, okay, if this is our answer, so we can say, okay, if we go to 5, we are at the leftmost point in the second row, or like, yeah, second row, basically. And then we can say that, okay, it's -1 because we are out of bounds again. We have actually come from left, so if we go back to right, it will be actually going to the visited set again, or visited node again, and this will lead us to 8. And if we go to up, again it's 0, and down is also 0. Similarly for 7, we can see that, okay, we don't end up in any proper state. And if we go to 6, again from 8, that means we are going up. We actually are in the visited set, so we actually backtrack again. So we eliminate these kind of possibilities, and then finally we go down to 9, which is like we go left, right, up and down. So it will be like 0 0, and if you go up, it's 8, and then with when we are out of bounds, we just return. So in this case, the only solution for us is like use what you say 6 can be the sum for us will be 23 in this case, right? The sum of these path which you have taken, and as discussed above, these sums will keep on changing depending on from where we are coming. It's not like similar to like some other dynamic programming problems we have seen. This is just a simple backtracking problem because we can come from any direction, and sum is sum. So it does not mean if you choose the maximum now or minimum now, but basically this sum will change. Now let's look at some another example. Like instead of starting with 6, we start from 7. We can see that right, up and down leads to nothing, because if we go to right of 7, we have no bound, we are out of bounds. If we go up and down, we just end up 0. So we just start from 7, then we go to 8. Now we can just see, can we go in all the 4 directions? And we can say, yeah, we can go to 5, 6, and 9, because 7 is already visited. And from 5, we can again, like we end up in no meaningful state from now on. But for 9, again, we will not end up in meaningful state, but at least we have visited it. So for us, this will be the answer. So it will be 7, 8, and 9, which will end up in this sum, which is 24. So now, if you look at it, we are actually looking at backtracking as some form of depth first search. But backtracking is more than depth first search, even though this solution uses DFS. But DFS is just one of the algorithms that can be used for backtracking. Now that we have understood this solution, let's jump into the code part. Code will be very similar to the DFS problems we have seen so far. So first thing we need to define is something called direction array. So we have to define it for left, right, up and down, right? So if we yeah, so we can define it as a what you say, two-dimensional array. So we can say that, okay, uh, for left it will be -1, like we will go like x in the -1 direction, and yeah, y will be -1, right? And x will be 1, right? So that's what -1 represents. Similarly for right, it will be opposite. So we will x will stay the same, but right will increment by 1. Then for up, x will be -1 and y will be 0. And change in x, I mean change in x and change in y, sorry, not x and y, yeah. And for going down, change in x will be 1, but y will be 0 again. Change in y will be 0 again. So now that we have defined this array, let's jump into the code part, and we can, yeah, just define this loop. Oh, sorry, not am, it should be grid dot length and int j equal to 0, j less than um, grid dot length, grid 0 dot length, j plus plus, right? And now we can define the answer that we want to return. So it will be max cold equal to 0 initially, let's say, and then it will be max cold of math dot max of max cold. And now we will start our DFS from all the nodes, right? So we will just say helper, we'll pass the grid and current I and j, right? And now that we have defined this, we will just return max cold. And now let's define our DFS function. So what we will need is a private int, because we will be returning the max cold for each step from the to the previous step. So we will just define it as we will pass in grid and int r for row and in c for column. Now we have this. First thing we will check is if we are out of bounds or if we have already visited this node. So what we can do is we can see how we can do this. Like, is if r is less than 0, right, or r is equal to grid dot length, that means we are out of bound now in terms of row. Similarly, if c is less than 0 and c is uh, equal to, what is say, grid 0 dot length, see, and then finally what we should also check is if the mine location has no gold in it. In this case it will be 0, so we will just return what you say 0 in this case, because we can't find anything in this case, so we will just return 0. Otherwise, what we will do is, like, I'll come to the part how we will take care of the visited thing. I mean, one easy solution could have been I could have passed a hash set and defined row and column some kind of a string, like as a, what is a key in the headset, and just have taken care of the visit. But what we can also do is, like, we can smartly think about, suppose we are doing the DFS from node 6 and we are going to 5, and if we want to sorry, we are going to 8, for example. Yeah, we can't go to 5, but if we are going to 8, for example, so when we are going up, how can we ensure that 6 is not there, right? So one way can be that I can actually set the value at 6 can be at 0. That is, I will destroy this gold mine and there's no gold remaining anymore because we have already taken it. And now when 8 goes to 6, it will find no gold and it will just return. But once I'm done with with this DFS, I will undo this solution. Another way can be that we can look at the constraint. So we can see, okay, the grid ij is less than equal to 100. So I can set it to say 100 or 101 or 1000 or something. And then I can also check it here that if grid rc is equal to say 1000, because that's what we are setting, we can actually also check it here. But in our case, we are just simply destroying the what you say gold mine temporarily and then fixing it. On my site, I've also given the solution, what you say, for the case where I'm using the hash set as well, but it's up to you, because we can also, if the interviewer is fine, we should actually we can actually leverage this technique. So now I've taken this gold as a backup for now so that I can fix it later on. And now let's destroy this gold mine. And let's go to calculating our max gold again. So at each step, what we can do is, like, from this point, if we are not satisfying any of this condition, that means we can actually collect the gold from this mine. And technically what we can now do is, like, we can just loop on our directions array and start going in all the four directions, right? So for us now, the new row will be what you say, r plus dir, what you say, I0, right? Because zeroth value is the change in x. And a new column will be c plus dir I plus 1, sorry, index 1, so which is change in what you say, y direction. So what we will now do is, like, we can just say max gold is equal to math dot max of what you say, max gold we had so far, and whatever this helper function can get us. So it will be create a new r and new c, right? And once we are done, we have to revert this gold array back. So what we will do is, we can say create rc is equal to gold. And now that we are done with it, we can just return our gold we have found so far. So it will be whatever gold we had in this mine plus whatever gold we got from the other remaining mines after doing the DFS from here. So it will be gold plus max gold, right? And now that we have done it, we will just yeah, return this answer, and hopefully we are done with this. So now let's run this code. Cool. So let's submit this code. Awesome. So I think it seems a bit slow, but now let's talk about the time complexity here. So if you look at it at each point, let's also open the, what you say, description. And we can see that at each point, we can have four directions to go to, right? 1, 2, 3, 4, like left, right, up, down. And this path will continue. So technically we have what you say, m into n nodes in this matrix, right? And wherever we find the goal, we start from it. So they have given this number of cells. So there will be at most 25 cells containing gold cells. So suppose, so technically our answer would have been m into n, because we are running this loop in m into n time. Then we are going in four directions, so that will take what you say, 4 to the power of m into n, right? That would have been our answer. But since m into n at maximum will be k, which is equal to 25, so our answer will be k times what you say, 4 to the power of k. And the reason for is, like, we at least at maximum will be 25, right? 25 cells which will be containing this gold. So if at most k cells are containing this gold, we will be having this time complexity. In terms of space complexity, here we don't have any issues, because we have what you say, we are just temporarily modifying the current grid, so it will be O of 1. But if we use the visited cell set solution, then the time complexity will be O of k again, because we are storing at most k values depending on how deep we go. I hope this solution was useful to you. If it was, please like and subscribe. Have a nice time. Thank you.